You know, in the world of manufacturing, there's one number that really defines everything, the ultimate yardstick for how productive you are: speed. And today we're diving headfirst into the ongoing battle to push that speed to its absolute limit. We're talking about something called the material removal rate, or MRR. To put it simply, it's how fast you can slice material off a workpiece. Think of it as the ultimate speed limit for production. The higher your MRR, the faster you're making parts, and, well, the more efficient your whole shop becomes. It's the one number everybody is constantly chasing. So that brings up a pretty obvious question, right? If speed is the name of the game, why don't we just crank all the dials up to max and let her rip? Well, it turns out it's not that simple. In machining, when you push for more speed, you're actually declaring war on some seriously powerful forces of nature. And here they are, your three main adversaries. Every single attempt to crank up the MRR is a direct fight against overwhelming heat, catastrophic tool wear, and immense cutting force. If you get even one of these wrong, your incredibly expensive machine just grinds to a dead stop. So, in this explainer, we're going to break down how the pros conquer them. Okay, so our battle really begins before the tool even makes contact with the metal. The very first big decision is picking the right environment, because the conditions of the cut itself, you can think of it as the battlefield, that has a huge impact on the heat and friction you're about to generate. You've basically got two main camps. On one side, there's dry machining. It's clean, it's cheap, it's better for the environment. But as research from folks like Rustam Binali has shown, running dry creates a ton of heat, which just fries your cutting tools and forces you to slow down. Then you have wet machining. You flood the cut with coolant, which is great for pulling away heat and cutting down on friction. That means your tools last longer and you can push that MRR higher. But it's expensive and it creates a lot of environmental waste. It was this exact trade-off that really pushed engineers to find a better way, a sort of middle ground. And that is where these incredible modern solutions like MQL come into the picture. Instead of flooding the part, MQL uses this high-pressure mist of air and oil, a tiny amount, to cool and lubricate right where the action is happening. It's really the best of both worlds. And you won't believe how effective these new techniques are. Just look at this number. Some fascinating research from Tahir Mahmood and Mohammed Shahid Khalil found that by making a microscopic change, just adding some special nanoparticles into that MQL mist, they could drop the temperature by over 17% while cutting super tough titanium alloys. That is a gigantic improvement from an almost invisible change. And less heat means a longer-lasting tool, less waste, and a faster, more sustainable process. And believe me, MQL is just scratching the surface. The modern toolkit for controlling the machining environment is just incredible. You've got high-pressure cooling that blasts away chips and quiets down tool vibration, cryogenic cooling that uses a liquid nitrogen for insane temperature drops, and even laser-assisted machining, which, don't worry, we'll get back to in a bit. Each one is a specialized tactic for winning that fight against heat. But controlling the environment is really only half the story. Even with the absolute best cooling system, the tool itself, your weapon in this whole fight, is under constant, brutal assault. Understanding and managing tool wear is absolutely non-negotiable if you want a high MRR. Every single cutting tool follows this exact, unavoidable life cycle. It starts out perfect, with a razor-sharp edge. But the second it hits the metal, the wear starts. At first, it's slow, but then it just takes off. The cutting forces spike, your efficiency tanks, and if you push it just a little too far, boom, the tool fails and your entire production line stops cold. The whole game is to keep that tool in the sweet spot for as long as humanly possible. And this quote just nails the central problem perfectly. As Guoxing Su and his team point out, tool wear isn't some simple thing. It's this complex soup of mechanical and thermal stresses all happening at once. The moment you push for more speed, you're directly speeding up that wear. So the secret to a high MRR isn't just about going fast. It's about going fast sustainably by finding that perfect, delicate balance. So what exactly is doing all this damage to the tool? Well, it's really an attack on multiple fronts. You've got abrasive wear, where tiny, hard bits in the workpiece are basically acting like sandpaper on your cutting edge. There's crater wear, where the crazy heat and pressure on the tool face literally just scoops material out of it. And then you have something called built-up edge, where bits of the workpiece actually weld themselves onto the tool, completely messing up its geometry and just killing your efficiency. Okay, this brings us to our final adversary, which is, let's be honest, the root of all our other problems: the fundamental physics of the cut. To truly become a master of MRR, you have to get a handle on the mind-boggling forces and temperatures that are at play. It's really a classic vicious cycle. To cut faster, you've got to push harder, which jacks up the cutting forces. Higher forces mean more friction and more deformation of the metal, which creates a massive amount of heat. And as we just saw, that heat is what absolutely destroys the cutting tool. See? It's all connected. The only way to win is to break this cycle by changing the physics of the fight itself. So how on earth do you do that? Well, say hello to laser-assisted machining, or LAM. This is such a brilliant strategy. A super high-powered laser is aimed right at the workpiece, just milliseconds before the cutting tool gets there. It heats up a tiny spot and softens the material, making it almost like cutting through warm butter. The tool is no longer fighting against hard metal, it's slicing through softened metal, which takes way less force. And the results are just staggering. Research from Farhana Yasmian showed that using LAM to mill stainless steel dropped tool wear by over 38%. But that's not all. Get this. It also improved the surface finish by almost 50%. So you're not just cutting faster and saving your tool, you are literally making a better part while you do it. That is a total game changer. And this idea of control applies even on a much smaller scale. Work by Osman Shaheen and his colleagues shows that even something as simple as the temperature of your coolant makes a real difference. Colder coolant is just more efficient at sucking heat out of the cutting zone. This keeps the tool edge more stable, which helps stabilize the cutting forces and lets you hold a higher MRR for a longer time. Every little detail matters. So, we've stared down our three big adversaries: heat, wear, and force. What does the winning strategy actually look like? How do we put all these tactics together to finally reach the peak, the highest possible material removal rate? At the end of the day, what's the big takeaway here? It's that there is no magic fix. There's no single silver bullet. You can't just go out and buy a fancier tool or a new kind of coolant and expect to suddenly double your speed. No, winning the battle for MRR demands a complete, integrated strategy. You have to master the environment, you have to actively protect your tool, and you have to intelligently control the physics of the cut, all at the same time. And this right here is what the modern playbook looks like. You've got the challenge of intense heat and friction. You hit it with advanced cooling like cryo or MQL. To fight back against rapid tool wear, you obsessively optimize your cutting parameters and your tool geometry. To conquer those massive cutting forces, you bring in game changers like laser-assisted machining. And to do it all without hurting the planet, you lean on smart, sustainable solutions like MQL. It's a complete, modern system. Which leaves us with a really fascinating question to think about. We're constantly engineering newer, stronger, tougher materials for everything from jet engines to medical implants. And these new alloys are ridiculously hard to machine. So the big question is, as the materials keep getting tougher, what kind of new weapons and new tactics are we going to have to invent to keep winning this never-ending battle for manufacturing speed? Thanks for joining me.